At the end of the last video, I asked the question, what happens if du does not match exactly with whatever we have left over in our integrand? And the short answer is we need to be a little bit more creative or just adjust it a little bit. So let's do a few examples of that. So say, for example, we wanted to know what is the antiderivative of 1 divided by 2x plus 3 with respect to x. Well, again, the first thing is we need to figure out is, well, what is u going to be, if it is indeed going to work at all. And so, one sec while I get my tablet in order. Okay, well, it's going to have to be good enough. Okay, sorry, I was trying to erase. There we go. But so, you know, in this case, again, if this were 1 divided by u, then we would know the antiderivative right away to be the natural log. So let's just go ahead and say if we were to set u to be 2x plus 3, then our integrand would be 1 divided by u. But again, that wouldn't help us with, well, we also need to change dx to whatever it might be. So again, if we were to figure out, well, du is the derivative of both sides, derivative of 2x would just be 2 dx. And the derivative of 3 would be 0. So here it's pretty close. The only issue is, well, du is equal to 2 dx, and we don't have a 2 within our integrand. So what do we do? Well, in a very similar way, we could divide both sides by 2. This would leave us with du divided by 2 is equal to dx, and actually solve for what dx would be. And then perform the simplification after solving for dx. Now, you don't always want to do this, but sometimes it can be a nice trick. And so we'd have, well, du divided by 2 would be equal to dx. And now my entire integral is changed to terms of u. And like we did in the very first video, du divided by 2, that's just equal to 1/2 du. And we could pull that 1/2 through the integral symbol, which would leave us with 1/2 antiderivative of 1 over u with respect to u. And now that we have, you know, it as one of our base forms, we know the antiderivative of 1 divided by u is just the natural log of u. So we'd have, well, 1/2 times the natural log of u, technically absolute value, and again plus c, because we're always, you know, or in these examples we've always been working with indefinite integrals. And then last step, as always, is to resub back in our x. So u is equal to 2x plus 3, so we'll go ahead and plug that back in. And now we are done. So in that case, basically the only thing that we had was an additional factor of 1/2 that came through from the fact that du gave us an extra factor of 2. And what you'll notice in the antiderivative is we have the reverse factor 1/2 coming through. Similarly, say we wanted to know the antiderivative of 6x minus 1 or 5x plus 7, it would be very similar. And I'll let you try those two on your own. But you should just end up getting a 1/5 and a 1/6 out front as the only difference in those examples. Let's look at one more. Let's say we had the antiderivative of x divided by the square root of x squared plus 81, all of that with respect to x. And again, here I would expect to set the bottom equal to u, or actually what I would probably do here is set the interior to be equal to u. Now, sometimes you can actually take the entire root and set that to be u. In certain cases, that will help, but you'll see why setting just the interior of the radical, the radicand, just setting that equal to u is nice here. Because if we were to solve du, that would be 2x dx. And again, notice it's very close. I have x dx, but I don't have the 2. So what I could do is divide both sides by 2 and solve for x dx. Now I have x dx, that's equal to du over 2. And again, I could even rewrite this, but I'll go ahead and skip that. And then I have 1 divided by the square root of that, which is just u. So again, kind of rewriting this, I have, well, 1 divided by the square root of u. And then x dx is equal to du over 2. And like we've been doing the past couple examples, I could pull 1/2 out. And I could even rewrite this because this is involving radicals and division. Well, this is u to the minus 1/2 power. And now I could just use the power rule to integrate or find the antiderivative of 1 divided by the square root of u. And then all I have on the outside is this additional factor of 1/2. Now, in order to find the antiderivative by the reverse power rule, I would want to add 1. So that would put me at u to the 1/2 and drop the reciprocal. So the reciprocal of 1/2 is 2, so I'm going to get an extra factor of 2 coming through there. And again, plus c because this is indefinite. And at the end of the day, this one, 2 and 1/2 will cancel, so we can often simplify our answer, and u to the 1/2 is just equal to the square root of u. So actually the answer ends up being quite simple here. I get the square root of u plus c. And then I could, as always, plug back in what u is in this example into my answer after anti-differentiating. So to sort of summarize this process, first step, pick u. Solve du, step 2. And then step 3 is to make sure your whole integral will converge. Sometimes you might need to do things like dividing both sides by 2 or playing around a little bit with the algebra of your U substitution. Often I like to write this on the side because it's not a part of my equation or my integral solving process, but it's sort of like my notes about what is happening in my substitution. And notice I'll kind of draw it off to the side in a lot of these examples. I haven't actually been kind of putting it into a box, but some people actually build a box, and there's a very specific way you can do this if you want. But I like to follow the basic idea instead of a very specific procedure, because not every U substitution problem will work in exactly the same way. And in the next video, we will discuss what can happen what if it's definite integrals, and how do we adjust in those cases.